Okay, so we're going to pick up with lesson 7 at compounding interest n times a year at an annual rate of r. So before we get into the formula in examples 3 and 4, I just want to go over a basic example to explain compounding n times a year. So let's go back to our example of depositing that $1 in January. If we were compounding semi-annually, and this was based off the example we looked at yesterday that had a rate, an annual rate of 12%. What that would look like is instead of having that 12% rate added to your money at the end of the year one time, which that example led our dollar in January to becoming $1.12 at the end of the year. If we were compounding the money semi-annually, what's happening is we're taking that rate of 12% and we're dividing it by 2. So we're getting 6% added to our money halfway through the year, so let's say the end of June, and that dollar is going to be now added to 0.06 times 1, or 6 cents added to the dollar. And then at the end of the year, we get the other half of our 12%, or the other 6% added to our money. So now that other 6% is getting multiplied with the 1.06, which is how much we have going into the end of the year, since our money was already compounded halfway through this year. So it's not that this end result is much more than our $1.12 from the first example. It's just that it grew a little bit more because the money was compounded twice in the year. Now what if we looked at an example where our money was compounded quarterly? So if our money is going to be compounded quarterly, now our 12% is being applied to our money 4 times a year. So if we break up the 12%, divide that by 4, we would get 3%, and that 3% is going to get added to our money 4 times throughout the year, or the end of each quarter. So technically, if you did take the year and break it up into 4 quarters, the end of March would be the end of the first quarter. So I'm going to end up with $1.03 by the end of March. Then we'll take that 3 cents and we will add it to our money at the end of June, which is the second quarter. So now I'm at $1.06 and a little more. Then at the end of September would be the end of the third quarter. So I take that 3%, multiply it with my 1.0609, and I get a little bit more than $1.09. And then by finally the end of the year, or the fourth quarter, I take that 3% one last time and add it to our money. And now I'm actually at the point where if I did round, I would end up with $1.13. So I am growing my money significantly more when I compound more. Maybe not significant, the word here to use, because we're only using $1 as our deposit amount or our principal amount, but our money is growing more the more times we compound our interest rate over the year. So let's look and see how that affects our formula. So our formula that we worked with yesterday, which was compounding just annually, which is really 1 time a year, was A equals P times 1 plus R to the T. So T represented time, R was our annual interest rate, P was the principal amount, A is the amount over time. So here, what's changing? So now we have n times a year at which we are compounding our money. So the rate is getting divided by n. So for semi-annually, we divided our rate of 12% by 2, and we got 2 6% rates being added to our money. And how many times did that happen? It happened twice in the year. So n is multiplying our time in the exponent, and it's also dividing into our rate. So let's take a look at example 3 and see if we can put this together. So we're given $5,000 to be put into a savings account. It pays 3.5% interest compounded monthly. So here's our interest rate, here's our initial amount. We're being compounded monthly here with our rate. How much money to the nearest 10 cents would be in the account after 6 years, assuming nothing was added or withdrawn? So let's just think about what we have here. So our initial amount, or P, is our $5,000. Our rate is 3.5%, which really would be, if you divide that by 100, 0.035. Compounded monthly, there are 12 months in the year, so that's n, that's the new part of the formula. And 6 years, that's our time, so t is 6. So let's plug into this. So we have a equal to 5,000 times 1 plus our rate, which is 0.035. Now this is happening monthly, so it's going to get divided by 12. And it's raised to 12 times the time period, which is 6 years, so 12 times over the 6 years. So now let's go type that in. I'm just going to take my calculator. Okay, so we have 5,000 times 1 plus, you can open up a fraction if you want, 0.035 over 12 raised to the 12 times 6. Now, it did say round to the nearest 10 cents, so that would be here. The 0 would not round up the 5, so it would be 6,166.50 or 50 cents there. Right, so it was 50. I'll just write the number before because we didn't really get to write there. And we're rounding to the nearest 10 cents, which means this is the place we're trying to round to, so the 0 would not round that up. So it's 6,166.5. Okay, now let's try number 4. So Seth's parents give him $5,000 to invest for his 16th birthday. He's considering 2 investment options. So option A will pay 4.5% interest compounded annually. So that's like what we did earlier in this lesson, where we did not have to think about how many times in the year because it's just one time. Option B will pay 4.6% compounded quarterly. So option A is the formula we used at the beginning of the lesson, A equals P times 1 plus R to the T. And option B is using the formula where we have n times a year being compounded, so 1 plus R is being divided by n, and the time is being multiplied by n. In both of these options, we are investing 5,000. So let's say for A, it would be A is equal to 5,000 times 1 plus our interest rate, which is 0.045, and they want us to use n for the time, so we'll use n instead of t. B would be 5,000, and we have 1 plus, now this interest rate's a little different, it's 0.046, but it's being compounded quarterly, so I need to divide this by 4 and raise the time period to 4 times n. So that was the first part, right? A function for option A and option B that calculates the value in the account over n years. Now it says Seth plans to use this money after he graduates from college in 6 years. So now we actually have our time, which in this case is our n, so n is 6. Determine how much more money option B will earn than option A to the nearest cent. So let's plug in the time into both of our formulas, plus 0.045 to the 6th, and B is equal to 5,000 times 1 plus 0.064 to the 4 times 6. Okay, so option A, we had 5,000 times 1 plus 0.045 raised to the 6th. Option B, we have 5,000 times 1 plus 0.046 over 4 raised to the 4 times 6. Okay, now how much more did option B? So let's find the difference. Option B minus option A, and to the nearest cent, this would be $67.57. So option A, just to write this down here. So option A was $6,511 and about 3 cents. Option B was $6,578.80. And when we subtracted B minus A, we got $67.57 rounded to the nearest cent. Okay, I hope this video was helpful to get through the rest of lesson 7 and to understand compounding interest n times a year. Please now try homework 7. Homework 7 we will go over on Monday, and the submission will not be due until Monday. Have a great weekend, everyone.